A study published in 2026 found that the missing heat extends down through the ocean, while the region is actually releasing less heat to the atmosphere than it once did. The surface is cold because the ocean below is carrying less heat into the area, not because the sky above is simply pulling more heat out. That changes the meaning of the blob. For decades, scientists have watched this patch of the subpolar North Atlantic resist the warming seen across nearly every other part of the planet. It is often called the North Atlantic warming hole, or the cold blob. The name sounds local, almost harmless, as though one corner of the ocean simply failed to warm with the rest. The new evidence points to a deeper reorganization. Observation-based reanalysis extending back to 1955 shows a decline in the region's full-depth ocean heat content. Satellite-era data beginning in 1993 show that surface heat loss did not intensify enough to explain the cooling. In fact, it decreased. The process responsible for the cold blob is therefore not confined to weather passing over the sea. The ocean is delivering less heat from elsewhere. That is exactly the kind of fingerprint scientists expect when the Atlantic Meridional Overturning Circulation, or AMOC, weakens. This enormous system carries warm, salty upper ocean water northward, releases heat across the North Atlantic, and returns colder water southward at depth. If that transport slows, the region south of Greenland receives less imported heat even as greenhouse gases continue warming the planet around it. The original title needs 2 repairs before the story can go any further. First, the cold blob is not suddenly performing one new action in August 2026. It is a long-term pattern whose mechanism has become clearer through new research. Second, scientists have not announced that the AMOC is collapsing now. The evidence supports weakening heat transport and a historically weaker circulation, but the distance to any tipping point remains uncertain. The strongest defensible title is more specific. The cold blob south of Greenland runs deep, and scientists link it to a weaker AMOC. The word deep is literal. The cold anomaly is not merely a thin skin of water reacting to a windy season. It involves heat content below the surface, which means the ocean has been reorganizing how energy enters, leaves, and accumulates across the subpolar Atlantic. For documentaries that follow the mechanism beneath a familiar climate image, subscribe and stay with us. The central question is not whether the cold blob exists, it is why a warming planet has created a region where the ocean has failed to warm, and what that tells us about the current system carrying heat toward Europe and the Arctic. Begin with the geography. The cold blob sits mainly south of Greenland and Iceland, inside the subpolar North Atlantic. This is where warm water arriving from lower latitudes encounters cold air, loses heat, becomes denser, and helps feed the overturning circulation. The area is not a single circular pool with a fixed edge. Its exact outline changes by season, dataset, and the time period used to calculate the trend. The long-term signal is what matters. A 2025 study compared historical observations with dozens of climate models. Only the models that produced a weaker historical AMOC could broadly recreate the observed combination of cooling and freshening south of Greenland. Models with a strengthening circulation generally warned the same region instead. The researchers estimated that the real AMOC weakened between 1900 and 2005 by roughly 1 to 3 sverdrups per century. 1 sverdrup equals 1 million cubic meters of water moving every second. Even the lower end represents an enormous change in the amount of ocean transported through the system over time. That number is a reconstructed trend, not a direct measurement covering the entire century. Direct continuous monitoring at one key Atlantic latitude began only in 2004, far too recently to isolate a clean centennial signal from natural variability by itself. The cold blob fills part of that observational gap. It acts as a fingerprint because heat transport leaves a spatial pattern. When less heat moves north, the subpolar Atlantic cools relative to the warming world, while waters near the Gulf Stream and the northeastern American shelf can warm more rapidly. The pattern is not proof from one pixel. It is a basin-scale contrast supported by temperature, salinity, subsurface structure, models, and direct current observations. The ordinary interpretation says the cold blob is a patch of cold water. The critical exception is that it may be the visible surface of a circulation change extending thousands of meters below. The map is showing a symptom. The contrast is visible across more than one dataset. Long-term surface records show cooling or a pronounced lack of warming in the same broad region, while salinity observations show freshening. The 2026 study then added the missing vertical dimension by examining heat stored through the ocean column. That matters because surface maps can be deceptive. A cold winter, a strong wind pattern, or a shallow mixed layer can temporarily paint the ocean blue. A full-depth heat content decline requires energy to be missing from a much larger volume of water. It is harder to create, slower to reverse, and more directly tied to transport between regions. The blob is therefore not one frozen moment, it is the accumulated result of heat moving differently through the Atlantic over decades. That distinction turns a cold patch into evidence about a changing circulation. The heat budget reveals the system behind it, and that is where the argument becomes physical. An ocean region changes temperature through three broad pathways. Heat crosses the sea surface, currents carry it across regional boundaries, and the water column stores the resulting difference. The water can then store the difference by warming or cooling through depth. For years, two explanations competed. One said stronger winds and colder air were extracting more heat from the surface, leaving colder water behind. The other said ocean circulation was importing less heat, so the region had less energy available to release into the atmosphere. The 2026 analysis tested those pathways with observation-based records rather than relying on one idealized model. If increased surface cooling caused the cold blob while ocean transport stayed unchanged, surface heat loss would have needed to rise enough to overwhelm the incoming heat. The data showed the opposite. Since 1993, surface heat loss over the cold blob region decreased significantly. The ocean was not cooling because the atmosphere had become a stronger refrigerator. It was releasing less heat because less heat was being supplied to it. That is why the full depth result matters. A weather-driven surface anomaly can appear and disappear with a season. A decline in heat content through the water column records a change integrated over years and decades. It points toward ocean transport, mixing, and circulation rather than one temporary atmospheric pattern. The AMOC is often described as a conveyor belt, but that image can be misleading. It is not one narrow current with an on-off switch. It is a three-dimensional system made from the Gulf Stream, boundary currents, broad interior flows, wind-driven gyres, deep water formation, and the return of cold water southward beneath the surface. The subpolar gyre sits inside that system. Warm and salty water flows north and east into the region. It releases heat, mixes with colder and fresher water, and moves through seas around Greenland, Iceland, and the Labrador Basin. Some water becomes dense enough to sink and contribute to the deep return flow. Density is controlled mainly by temperature and salinity. Cold water is generally denser than warm water. Salty water is denser than fresh water. Cooling can encourage sinking, while fresh water from rain, sea ice, rivers, and Greenland melt can make the surface lighter and more resistant to mixing downward. This is where Greenland enters the story. The ice sheet and its fjord glaciers release fresh water into the North Atlantic. That meltwater does not travel as one simple cap across the entire basin, and its effect depends on winds, eddies, fjord geometry, ocean state, and where it enters the circulation. Scientists are still measuring how efficiently it reaches the places that influence deep mixing. In July 2026, an international team began a 6-week expedition to southeast Greenland as part of the giant project, Greenland Ice Sheet to Atlantic Tipping Points. Researchers aboard the RRS Sir David Attenborough are using drones, satellites, autonomous boats, underwater robots, and direct sensors to measure glacier retreat, fjord depth, temperature, salinity, currents, and melt near submerged ice faces. The mission exists because one of the most important links remains poorly observed. Scientists can measure Greenland losing ice at large scales. They can measure salinity and circulation farther offshore. The difficult part is tracking freshwater through chaotic fjords, around icebergs, into the subpolar gyre, and eventually toward the regions where water exchanges heat and sinks. A fjord is not a pipe. Fresh meltwater can remain near the surface, mix downward, become trapped by circulation, or exit in pulses. Warm ocean water can enter beneath colder surface layers and melt a glacier from below. Icebergs and sea ice can temporarily slow the glacier front, then clear in summer and allow faster calving. These processes operate from meters to entire ocean basins. That range is why researchers are deploying instruments capable of working close to a 100-meter ice cliff and robots that can dive more than a kilometer beneath floating ice debris. The observations will help determine how Greenland's freshwater and the subpolar gyre interact before the signal reaches the broader AMOC. Freshwater is one pressure on the circulation, but it is not the only control. Atmospheric warming reduces the ocean's ability to lose heat. Wind patterns alter currents and upwelling. Sea ice change affects salinity and surface insulation. Conditions in the Southern Ocean influence how much deep water must return northward. Internal variability can strengthen or weaken the system for years at a time. This complexity explains why one study can find serious warning signals while another finds that complete collapse before 2100 remains unlikely. They may be asking different questions. A circulation can weaken substantially without shutting down. A cold blob can strengthen as a fingerprint without proving that a threshold will be crossed in a specific decade. A model can preserve some northern sinking while still producing major regional climate changes. The cold blob, therefore, does not function like a countdown clock. It functions like a stress indicator. The 2025 historical study found that cooling and freshening were not limited to the sea surface. In weakened AMOC model groups, the signal extended through the deep-water column, matching the broad structure seen in observations. Reduced northward heat transport created a divergence. Less heat entered the subpolar region than left, or was redistributed within it. The atmosphere partially pushed back by warming the colder ocean surface. That feedback is easy to miss. The cold blob is not cold because the atmosphere relentlessly extracts heat. Once the sea surface cools, the atmosphere can actually deliver heat back toward it. Yet the region still remains anomalously cold because the missing ocean transport is larger than that compensation. The ocean is losing the supply battle. That is the one action the new research clarifies. The cold blob is not simply giving more heat away, it is receiving less heat from the Atlantic circulation. The consequences do not remain south of Greenland. The Atlantic distributes heat in a pattern, so a change in transport creates winners, losers, and unexpected contrasts around the basin. The cold blob can deepen while waters closer to the Gulf Stream and the northeastern United States warm. The current can shift position as its larger circulation changes, altering ocean temperatures along continental shelves where ecosystems and coastal economies are already sensitive to small changes. This dipole is part of the fingerprint. Cold south of Greenland does not mean the entire North Atlantic is cooling. It can coexist with rapid warming nearer North America and unusually warm seas elsewhere in the basin. That is why a global map can show both record ocean heat and one persistent blue patch without contradiction. The heat has not vanished, it has been redistributed. A short-lived circulation downturn in 2009 and 2010 demonstrated how quickly that redistribution can reach the coast. Tide gauges from New York City to Newfoundland recorded an average sea level jump of about 100 millimeters over the 2-year period. The event was linked partly to an observed 30% downturn in the AMOC and partly to an unusually negative North Atlantic oscillation that pushed water toward the coast. The example needs careful limits. It was not a permanent collapse, and the circulation recovered from the extreme downturn. The sea level event had more than one cause. It does not mean every AMOC fluctuation will raise coastal water by the same amount. What it proves is that circulation changes can alter regional sea level on human timescales. The Gulf Stream and associated currents help maintain a slope in the ocean surface across the western North Atlantic. When the circulation changes, that dynamic balance changes. Water can accumulate differently along the continental margin, adding to or subtracting from global sea level rise at particular coasts. For cities, the consequence appears as higher baseline water from which storm surges and high tides begin. Drainage systems must also push water against that elevated starting point. Even a temporary circulation-driven rise can increase the frequency of coastal flooding when it overlaps with storms, tides, and the long-term rise caused by warming oceans and melting land ice. The cold blob is therefore connected to a coastline hundreds of miles away through the same heat and pressure fields that shape Atlantic currents. The biological consequences follow temperature boundaries. Fish, plankton, shellfish, and predators respond to where suitable water moves, not to national borders. A northward shifted Gulf Stream and changing Labrador Current can rearrange the boundary between warm and cold species along the northeast U.S. shelf and the Gulf of Maine. Some populations move, others lose habitat, encounter new predators, or become separated from the timing of their food supply. This does not allow one fishery decline to be assigned to the AMOC alone. Fishing pressure, local management, marine heat waves, acidification, oxygen, and natural variability all matter. The circulation changes the background on which those pressures operate. Europe faces a different balance. The AMOC carries ocean heat northward and helps shape temperature and rainfall across the North Atlantic sector. A weaker circulation does not mean Europe suddenly enters an ice age while the world warms. Greenhouse gases continue adding heat to the climate system, and the final regional temperature depends on the competition between global warming and reduced ocean heat transport. The result can be slower warming in parts of northwest Europe, altered precipitation, shifting storm tracks, and different extremes compared with a world where the AMOC stays stone strong. A complete collapse would create far larger changes than a gradual weakening. That distinction is the midpoint of the story. The cold blob is evidence that the circulation has changed, but it is not proof that the most extreme future has begun. Direct observations reinforce both the concern and the uncertainty. The rapid array has measured the overturning circulation near 26.5 degrees north since 2004 using moorings that track density, currents, and pressure from the Bahamas to Africa. The public dataset now extends through 2024. 20 years is a major scientific achievement. That record is already long enough to reveal the circulation's enormous year-to-year swings, but not long enough to turn every change into a centennial verdict. It is still short compared with the decades of natural Atlantic variability and the century-scale trend researchers are trying to detect. A strong year does not erase long-term weakening. A weak year does not prove a tipping point is imminent. The array also measures one latitude, while the AMOC is a basin-wide system whose components can change differently. The Deep Branch, Upper Branch, Gulf Stream, subpolar gyre, and Southern Ocean connections do not all respond at the same speed. This is why scientists combine evidence rather than searching for one decisive gauge. They use moorings, satellites, Argo floats, hydrographic surveys, tide gauges, sea surface temperature, salinity, deep ocean heat content, paleoclimate records, and models. Each observes a different piece of the same circulation. The cold blob is powerful because it integrates several of those pieces into a visible pattern. It contains cooling. It contains freshening. It extends below the surface. It sits where reduced northward heat delivery should leave a mark. Yet even that fingerprint must be interpreted beside atmosphere-driven variability. Winds can shift the gyre. The North Atlantic Oscillation can change heat loss and current pathways. Volcanic aerosols and industrial air pollution can temporarily alter the regional energy balance. The strongest conclusion is not that every cold year proves collapse. It is that the century-scale warming hole is difficult to reproduce without a weaker historical overturning circulation. The blob is not a forecast. It is a record of what the Atlantic has already been doing. What happens next depends on how much the circulation weakens, how fresh water enters the system, and whether stabilizing processes remain strong enough to prevent a transition into a much weaker state. The AMOC has a tipping point in physical models because the circulation helps maintain the conditions that support itself. Warm, salty water moves north, then cooling increases its density until some of it sinks and helps complete the deep return flow. Freshening can weaken that feedback because lighter surface water resists sinking. A weaker circulation then transports less salt northward, which can leave the high-latitude Atlantic even fresher. Under some conditions, that feedback allows the system to shift abruptly into a weak state rather than declining smoothly. The existence of that mechanism is well established. Its distance from the present climate is not. A 2025 study led by the Met Office and University of Exeter examined 34 climate models and found that complete AMOC collapse before 2100 was unlikely, even under extreme warming scenarios. Southern ocean winds continued driving upwelling that required some compensating sinking in the North Atlantic or North Pacific. The same study did not find safety in the status quo. It concluded that the AMOC is very likely to weaken during this century, and that the weakening would create important climate challenges for Europe and beyond. Its result supports the latest major assessment that an abrupt collapse before 2100 is not expected with medium confidence. Other studies read the warning signals more urgently. They identify changes in temperature, salinity, variance, recovery time, and freshwater transport that may indicate a circulation losing stability. The 2026 Cold Blob paper argues that strong evidence for historical weakening is a serious concern because further weakening could have effects lasting for millennia if a threshold were crossed. These findings are not mutually exclusive in the simple way headlines often suggest. One group can find collapse unlikely before 2100, while another finds the system weakening and displaying concerning fingerprints. Unlikely does not mean impossible. Weakening does not mean collapse. A tipping point can exist even when scientists cannot locate the present system precisely relative to it. Risk depends on both probability and consequence. The system also has inertia. Ocean circulation responds slowly because it involves enormous masses of water and exchanges between the surface and deep sea. That inertia can delay visible consequences, but it can also make a major shift difficult to reverse once established. That is why Iceland, the United Kingdom, European research agencies, and ocean observing programs are treating the circulation as a planning problem rather than waiting for scientific certainty about a collapse date. The July 2026 Greenland expedition represents that approach. Researchers are not sailing toward Kangerlussuaq Fjord because the cold blob predicts an immediate shutdown. They are trying to measure the missing link between glacier melt, fjord circulation, the subpolar gyre, and the broader overturning system while the changes are still unfolding. The tools reveal the scale of the uncertainty. A sensor can drill into an ice face 100 meters below the surface to measure melting directly. Surface robots can map the submerged glacier front. Coordinated underwater vehicles can sample temperature and salinity near unstable ice. A long-range autonomous submarine can dive beneath dense iceberg melange and map conditions more than a kilometer down. Those observations will answer questions that satellites cannot. How much warm water reaches the glacier? Where does the resulting freshwater go? Does it remain in the fjord, mix downward, or escape rapidly into the coastal current? How does the timing change between winter and summer? Which pathways carry fresh water toward the subpolar gyre and which disperse it before it can influence deep mixing? The answers will improve models, but they will not produce a date for an AMOC tipping point. The monitoring problem is too large for one expedition. Moorings can fail. Robots can sample only part of a fjord. Satellite measurements see the surface better than the deep ocean. Direct AMOC observations span decades, while the circulation varies across centuries. This is why maintaining observation systems matters. A climate tipping point cannot be managed through occasional snapshots. Scientists need uninterrupted records long enough to distinguish a trend from a cycle, and broad enough to connect Greenland, the subpolar gyre, the Gulf Stream, the deep Atlantic, and the Southern Ocean. The cold blob is one of those records. Its current scientific meaning can be stated without turning it into an emergency alert. The North Atlantic south of Greenland has cooled relative to the warming planet. The center has cooled significantly in long-term datasets. The heat content decline extends below the surface. Surface heat loss does not explain it. Reduced ocean heat transport provides the stronger mechanism, consistent with a historically weakened AMOC. What it does not prove is equally important. It does not show that the Gulf Stream has stopped. It does not mean Europe will freeze next winter. It does not identify a collapse year. It does not allow one storm, drought, flood, or marine heatwave to be attributed to the AMOC by itself. It does show that climate change can produce local cooling through a disruption of heat transport, even while the planet's total energy continues rising. That contradiction is the title payoff. The cold blob is not evidence against global warming. It is one of the ways global warming can reorganize the ocean. Picture the North Atlantic on a temperature trend map. Nearly every ocean region is shaded toward warming. Near Greenland, one patch remains blue, surrounded by water and air accumulating heat. Now remove the surface. The anomaly continues downward through the water column. The atmosphere above is not extracting more heat. It is receiving less because the ocean below has imported less. Farther south and west, other waters warm as the transport pattern shifts. On a research ship near Greenland, robots disappear beneath iceberg-filled water to measure how meltwater enters that system. Thousands of kilometers away, moorings between the Bahamas and Africa continue recording the circulation one profile at a time. No alarm sounds when a current weakens by fractions of a spheredrup. The signal appears as a pattern accumulated across decades. A warm planet develops a cold scar. The frightening part is not that the scar exists. It is that the new evidence shows how deep it goes, and how much of the Atlantic must change to create it.